How was that meeting with the cosmonaut friend? I'm interested in hearing about that. I think it was a month ago when you mentioned it.
Um, yes, meeting my friend in Moscow was wonderful because basically he is getting ready for his third flight.
Wow.
And I will be there to say goodbye at Baikonur on December 8th when he will depart to the space station.
Wow.
And then I will be there to welcome him back on planet Earth on December 22nd in Kazakhstan, in the middle of Kazakhstan steppes. So
Yeah.
it will be interesting to see his third flight, how he is will be launched and docked to the space station, entering the space station, and with his crewmates. So it will be very interesting to observe and to participate in all of those events.
Did he
I
tell you?
think. Go ahead.
I was going to say, did he tell you about like what he's doing on the space station? What are his tasks? What's his main task?
Um, this will be his third flight and kind of short flight. The first two flights were for 6 months each,
Yeah.
and this one will be only for 2 weeks. So there will be some science operations. There will be some. He will be helping the crew on the space station to to conduct regular tasks. But his primary objective would be to fly two Japanese tourists to the space station.
Oh,
So this will be a commercial flight to the ISS by a wealthy Japanese individual and his colleague. So both of them will stay on the ISS for, I believe, 12 days, right? And so they are now undergoing very rigorous training before they will depart to the ISS. And that will be interesting because for him it's a it's a flight where in the cockpit typically you have three people flying in Soyuz vehicle. This time, and each of them are professional cosmonaut or astronauts.
right, right.
So basically, each of them will have very clear tasks during the launch and landing. So they will be operating some systems at the space vehicle. But this time, the two tourists are trained, but the primary responsibility to operate the vehicle will be on him. And you can imagine under significant, dynamical loads when the system is launched. For him, it will be quite a challenging task to operate the panels which are on the far left and far right in front of you. So there is a dashboard
Yeah,
in the
sure.
Soyuz vehicle, and the commander of the vehicle sits in the middle. And so for him, it will be rather easier to reach the middle section of the panel. But the sections on the left and on the right will be kind of difficult, and one may expect that the tourists will be capable of doing things. But in case of something happening, he would have to be able to operate that system manually himself. And so that is one of the most challenging tasks because typically, as I said, the Soyuz is operated primarily by three people. And so now he will have to be doing this by himself. But the flight that took place on October, I believe October 5th, when the two actors, one actress and film operator, flew to the space station when a friend of mine, Anton Shkaplerov, was commanding this vehicle. He was doing okay. So basically, I think it is now not a normal practice, but it was done recently. So when a person who flies Soyuz vehicle operates that vehicle on the left and on the right, it's quite different compared to SpaceX Dragon capsule,
Yeah,
where most of that is done automatically and with minimum intervention from the crew. So Soyuz still requires a little bit, manual engagement from the crew that flies it. And so in this case, it's a little bit different, but I think it will be all right.
Is this a friend from your time at the Soviet space program? Or
No. Usually you grow older, and you don't expect that you will meet people at your sort of middle age who will become your friends. And so in my case, that was exactly the situation. When I grew up, I never knew. I mean, those people were untouchables. They were so far away, basically. They're flying to space. You would never expect to meet them.
yeah,
And life goes by, and you're meeting those people, and you're getting very good friends. And so I met him about maybe 10 years ago. So, and since then, our lives are pretty much intertwined, and I'm happy that I have a friend like this.
yeah, and definitely want to touch on the fact that you were there at the Soviet space program, because not a lot of people were at the Soviet space program and NASA. So what are the differences between?
For me, going back to the Soviet Union, we're talking about 93, 94. I moved to United States exactly in 93. I wouldn't say I was in the Soviet space program. I was interested to be there, and of course, I traveled to the cosmonaut training center because at that time there was a call for cosmonaut scientists, and so I was hoping to fly one day on the among the crew members to the space station, or whatever space station at that time was in the Soviet Union. And so basically we underwent a little bit, preparatory training, but then this didn't happen because of, budgetary cuts, and then the Soviet Union ceased to exist. So a lot of things happened. But back then, it was space program was very exciting because there was a lot of funding, and it was ongoing and very interesting, because human space flight was pretty much, very well supported, and was high on the agenda of everybody. And so it was very nice to participate, because you are definitely part of the very interesting training procedures, and you're meeting interesting people, and you're going through an experience that you would never expect to go through. And so that was on a personal human space flight side. But on the robotic exploration, so back then in the Soviet Union, you can expect that there were plenty of missions going into different planets in the solar system. So there were some missions going to Venus. Recently, there was a flight to the moon, Lunar 1, Lunar 2, in late 70s. Then there was a missions to Mars. So the program was rather very well established. And back in the United States, I believe at that time, planetary exploration was not a very well established objective.
Okay.
And the Planetary Society, I realized that Planetary Society was trying to argue in front of Congress and NASA, trying to ensure that NASA will have a very well developed program of planetary exploration. And so 20 years down the road, you see that now NASA does pretty much everything in the solar system.
Yeah.
So there is no agency on this planet that does as much as NASA does. But back then, in late 90s, it was not the case. It was beginning of the shuttle. Sort of Apollo program was winding down, and then shuttle program was developing, but planetary exploration was not very well, presented on the agenda at NASA.
Sure.
But now, pretty much, I work at the Jet Propulsion Laboratory, the organization that actually flew missions everywhere in the solar system. So I can take the data, I can get the data from any planetary mission and process the data and get very interesting results. I can come up with any idea, and at some point, this idea may be tested in a space flight. So it's pretty exciting, because it's being in the process which actually often results in getting very interesting data. It's very exciting. So comparing my sort of participation in or being present in the Soviet Union when the program was ongoing and very well supported, it was interesting. It was exciting. But back then I was junior member of the science community. So now time flies, and I'm now sort of a member of the global science community in a sense, and I'm
Yeah.
very well represented here in the United States and both internationally. So in this case, I guess now I'm witnessing the development of very exciting, objectives in the planetary exploration and the astrophysics and the Earth exploration, because the new technology is being developed and the new opportunities came up. So I think there is no comparison really, because it's a very different stage of global space exploration we are witnessing today. And so I think in general, I just appreciate the fact that I'm being part of the larger community that is bringing space closer to everybody who lives on this planet. Because can you imagine, kids who are born today, they take space for granted. We fly to space regularly. We have not only professional cosmonauts and astronauts going to space, we now have tourists flying to space. So space flight is not something that is very remotely possible. Now we're talking about building space stations, commercial space stations. We are talking about landing on the moon and building colony on the moon. And so that is something quite unique and mind changing experience, because space is our daily life. Because when you take your cell phone and you are driving your car somewhere in the unfamiliar neighborhood, your GPS transponder allows you to locate yourself with very high precision. So that is given by the signals from global positioning system, that is number of spacecraft orbiting Earth. So that is space in daily lives. And now we are building Internet of Things. And so where small spacecraft will provide you with the status of, let's say, your fridge. If you don't have milk in your fridge and driving home, you can ask your fridge whether or not you need to pick up milk.
Sure.
And so the fridge will tell you, yes, you need to do this. Or when you're driving your autonomous car, when you're in your autonomous car, sort of driverless car, it's the satellite signal and the signal provided by the transponders on your highway will tell you where you are and how safe the environment is. So it's all due to space access.
Yeah, and with Elon's Starlink, that's going to be even, it's going to be even compounded more. It's gonna I don't know, he's sending record number of pods. I'm not sure the right word but satellites in line with each other up in. I think he's doing India now. So how do you think about Starlink and what Elon's doing?
There will be, I believe, 44,000 Starlink spacecraft. So, and those spacecraft are still being launched. There is no global coverage of the entire planet, but at some point there will be very dense coverage of the entire planet. So the constellation that is being deployed by Starlink is very exciting, because anywhere you will find yourself on this planet, you will be able to get not only your positioning, but rather broadband signal, internet signal. So you will be able to communicate from anywhere, from being on the sea, being on the train, fast moving train. So, which is, I live in the hills in Los Angeles. And so sometimes I don't get my internet signal here. So my broadband connectivity is limited.
Yeah.
But with Starlink, people who live in the mountain area somewhere in Colorado or in the Sierras in California, they will have very reliable signal. Last year, I took my daughter to a camping trip. We went to John Muir Trail in California. It's about 2 weeks high Sierra Trail going from Yosemite all the way to Mount Whitney. It took us 2 weeks
Nice.
to cover almost 285 miles. And so most of that area, you don't have any signal. You can
No.
have only emergency signal from emergency satellites, but you're going in the trail and you have no ability to communicate with anybody and to inform where you are. So it would be nice to have, Starlink terminal with us during that trip. But maybe, it's a choice. Back then, I really enjoyed to be disconnected from civilization. But at some point, you want to be connected.
That's a good point, actually, because the one thing that humans do love is being disconnected and going on trips like that. But at some point, it's going to be 100% of the surface area of the world is going to be connected in some way, whether you like it or not. That's a
You
good
can
point.
always switch off your phone.
Sure. Yep. You could or not bring it. Yeah.
Exactly.
Right. So that's and this is all these developments and innovations are dependent on us cleaning up low Earth orbit. I would say because as we talk about, there's a bunch of junk up there. How do you guys at NASA think of that?
We'll have to establish rules for driving spacecraft in space, and so
Yeah.
those rules are being established now. We need to maybe start enforcing them because space is getting very populated, densely populated. Especially early years of space exploration left us with a lot of junk up there. So there are some graveyard orbits where we park our spacecraft when they reach sort of the final days of their life. So we park them there because it's just convenient. But it's not enough because some spacecraft collide, some spacecraft really malfunction and they become junk. And so they now become space hazards because when you fly your spacecraft, you need to know positions of every communicating satellite, but not only every communicating, but those that don't communicate and those that you would like to avoid. And for example, when you fly humans, it's most important because space station quite often gets signals that a certain part of space debris is on a course on the trajectory of the space station, so the orbit of the space station need to be, changed to avoid collision, and some micro pieces of space debris hit space station. And when astronauts conduct spacewalks, they routinely see little holes in the solar panels because the micro, space station flies with a very high velocity. It's about 7 kilometers a second.
Yeah.
And so imagine if you have a piece of sand, let's say maybe couple millimeters in diameter only. So when that sand hits your panel, you just get hole through the panel because it's significant kinetic energy being deposited on the panel.
A sand grain?
I mean, even like 2 millimeters. So
Wow.
it vaporizes on the impact, and it releases a lot of heat, and actually you get little, puncture holes in the panels.
Yeah.
And so over the years, the space station will accumulate those little punctures. So
Yeah.
you need to be able to deal with them. And so when you deal with the safety of humans, you have to be very careful. But even when you deal with very expensive piece of equipment that we fly up there, spacecraft that monitor Earth, you need to be able to avoid collisions of those spacecraft with debris as well, because it's very expensive to replace that satellite. So it's really up to satellite operators to implement safety procedures to avoid space junk. But maybe the other way is actually to clean the orbit from that space, a lot of space debris,
Right.
and implement sort of safety highway procedures, right? You don't when you turn left, flash to the left. When you turn right, flash to the right, so that everybody know what you're doing. And basically, um, when you are in space, you have to be able to obey rules because this is something that will affect everybody. And
Do you
so,
think
go ahead.
do you think private industry is going to be doing this and creating the innovations that'll clean up or create shields for the stations, or both, or do you think government agencies are going to step up?
It is already doing that. There are many startups that are aiming to help to clean the orbits.
Yep.
And reality is that this is a very challenging problem, because you can clean a certain orbit, one orbit, but then you need to have maneuverability of your spacecraft in space. And usually, most of the fuel spent when you launch the spacecraft from the ground all the way to the orbit around Earth.
Yeah.
But when you are in orbit, you need to be able to maneuver and to work as a space dog. So this is where your propulsion capability will be important. Chemical propulsion is limited because you have expendable fuel. Once your fuel is sort of exhausted, you have no spacecraft becomes a piece of space junk. So you need to have something like a renewable energy. It may be ion propulsion or maybe solar electric. When you have the sun, abundant energy from the sun, and basically you extract the energy from the sun and you try to do something with that. So this way you can have a space dock with reliable and ensured space propulsion capability. This way you can actually start cleaning.
Yeah.
So there are many ideas to do that, but yet we have to see a commercially viable sort of business model. We don't have that yet. There are many proposals, and people are trying to, to develop new business models where cleaning space debris will be commercially viable. At this moment, I guess federal agencies are interested in sort of paying for those services, because somebody needs to do that. It's either government will be doing this or private industry.
Like a trash collector of space.
Exactly. It has to be done. And basically, somebody, but it's also a legal issue, right? You cannot come to somebody else's property and just take it, right? Although it is a space junk, or maybe it's space debris, it belongs to a nation that you don't want to come and take, right? So because it may create an international accident, right? You have to be very careful.
What are the boundaries of each country? How do they extrapolate?
It's not that. It's international space law. When you launch your spacecraft, it belongs to your nation, and so that nation has a responsibility to clean up after itself, or ensure sort of that nobody will come close and to approach your vehicle. So it's a set of laws that were set, I think, in 1967, I believe, but they need to be updated. There is an urgent need to update those international space laws, because we have so many spacecraft that are not operational, but they still belong to different nations, and you cannot come and take spacecraft that was flown by Italy, and you're a German company, also your neighbors,
I see.
you come and repossess the spacecraft. It just doesn't look nice, right? So although it's a space junk, you don't want to be cleaned up by somebody else. So there is a lot of legal issues.
Too much. China doesn't seem to care too much about their space and how it's impacting. We're based off of the recent news.
Right.
I've been seeing, yeah.
And I think, if there will be a service provider that will be able to clean up space, those nations that, have the old pieces of hardware flying, they maybe well ask that, provider to clean up their space. So their spacecraft. So there may be some different issues, but there is a way to do this collectively, and I think we have to do it. Another problem is that when spacecraft collide, because they do collide in orbit, and when they collide, they provide thousands of pieces of debris. There was a collision, I believe, a Chinese spacecraft hit a Russian spacecraft, and so it was a significant number of space debris, resulted from that collision. I think it's about 22,000 pieces, and so then it's easier to collect a spacecraft and sort of bring it back in the Earth atmosphere when it will burn on the reentry. But smaller pieces of debris, let's say maybe 5 centimeters, maybe 10 centimeters, it's harder to go after them. So it's really the technology that we will have to develop. We'll have to be able to clean very small pieces of debris, not only like meter size and maybe 50 kilogram in weight. They have to go down to maybe even, let's say, maybe 5 centimeters, maybe even 3 centimeters.
Well, how are we going to even track the small things? Are we going to have to bounce waves off them or something? I mean, we can't see it unless there's light bouncing off it itself.
There are some technologies that we have developed that allow us to see those pieces of debris at certain sizes. So
Yeah.
the larger the piece, of course, it's easier to detect it. And so because we use different techniques, it may be radio, maybe optical, maybe infrared. So those techniques have different sensitivities. And ultimately, we can see very small pieces of debris. And I believe U.S. Space Command is actually tracking a lot of pieces of debris in space, and this information is available. So each object that enters space gets its number, and so after when it enters the space, its orbit is being precisely tracked by multiple organizations, not only in the United States but other countries.
Okay.
And so sharing this information, I think, will be a first step to actually develop a global database for those objects. And then once we know all of them, at least those that we know, we have to be able to clean.
Theoretically, we can understand the orbital paths of these single items or large massive items and deploy a net in the path and then scoop that net back up and then deposit it somewhere else, I guess. But again, that we're gonna have to solve the propulsion issue. And ionization is nice, but it's not that there's not a lot of power output. So
The net is an interesting idea, but as we discussed, those pieces of debris they move with different velocities, and
okay,
so the kinetic energy that they carry, once they will be captured by the net, it will be sort of translated into thermal energy. And so during the impact, a lot of thermal energy will be released on that net, and so the net will burn.
right,
And we need to have a very different materials, maybe those that actually do not burn at very high temperatures, and then very few of those materials. Graphene may be one of them, but it's still technologically we are not there to have a net.
yeah,
So an easier approach would be, now every spacecraft that we launch has the Earth reentry requirement. When you fly something in Earth orbit, once your spacecraft finishes its primary science operation, primary mission operation, it has to sort of deorbit itself. And so when it's deorbiting and re-enters Earth atmosphere, and actually it's been burnt on the re-entry.
okay.
So those spacecraft, new launches are allowing us to deal with those pieces. But those spacecraft that are now in orbit, it's rather difficult to capture them. So we know their orbit, we know where they are, but
Okay.
going after each of them, it's
Yeah.
not that simple.
All right. I'll go back to the drawing board on the net.
Very
Yeah.
good.
Yeah, and I know light sails. In terms of, I mean, this wouldn't be useful for what we're talking about, but I know you mentioned it in terms of how we're going to get to 550 or 650 AU, which we'll talk about in a second. But light sails are interesting because it's using photons, and photons are abundant, right? So what do you guys and yourself? What do you think of light sails and how we're going to use that in the future?
Light sails are amazing technology because they do require, they do provide us pretty much endless propulsion capability if we are going nearby the sun at one astronomical unit distance, let's say Earth orbit, because we still have plenty of solar energy. And
Yeah.
so how do they work? They translate the solar radiation pressure when the photons are impacting your sails as a sort of a solar sail. They transfer momentum that photons carry. They transfer the momentum to the sail, and essentially that sail changes its velocity and orbit. So because we have abundant solar energy, we can potentially use solar sails to travel between Earth and the Moon and back. And the design that we have developed for solar sailing spacecraft allows us to use solar sailing spacecraft like a sailboat. A sailboat, as you know, can travel almost against the wind. So the solar sailing spacecraft can travel almost against the solar radiation pressure. So we can go all the way from Earth to Mercury and back using solar sails. it's a low thrust propulsion, but potentially we can do like Amazon delivery truck. We can travel between Earth and the Moon, carry different instruments when we deploy, or spacecraft around the Moon. When we start building something on the Moon, potentially we can use solar sails to travel between Earth and the Moon pretty much endlessly, because we can deposit photovoltaic elements on the sail. Therefore, we can get energy, not only propulsion but also energy, and we can shape those sails so that they can be used as a radio antenna. So here you go. You have endless propulsion. You have pretty much endless energy, and you can use the sails for communication. So when you travel between Earth and the Moon, it's really easy to deploy those solar sailing spacecraft. Again, low thrust, but they can be used like drones.
Yep.
So drones going back and forth, and it's pretty interesting. But solar sails are exciting technology not only because of this, but primarily because we can reach even higher velocities with solar sailing. As you are aware, the fastest ever flown spacecraft by humanity is Voyager 1 and also New Horizons. Both of them reached velocities of roughly 3 astronomical units per year. And here, 1 astronomical unit is the distance between Earth and the Sun. With solar sailing, we can reach potentially velocities 7 to 10 times faster. And so imagine with velocities of 20 AU per year, we can go to Pluto in 2 years. And so we can access any object in the distant solar system in realistic time, not decades, but we can talk, 3 to 5 years, we are way behind the solar system.
Yeah.
We can start thinking about, rendezvous with interstellar asteroids that are visiting our solar system, because no other technology allows us to actually contemplate the idea of meeting with those interstellar asteroids, potentially landing on them, and travel interstellar with the spacecraft. Imagine with solar sailing spacecraft, you can land on an interstellar asteroid and embark in your interstellar travel. So it's possible today. So interstellar travel that we think about, we can go. We all think about Enterprise from Star Trek. We get the Enterprise spacecraft that goes, everywhere, but that's science fiction. I'm talking about reality. Today, with interstellar asteroids that are visiting, we can land on one of them and actually send a message to nearby stars that we are here and we are friendly and we would like to contact you. So it's something that Carl Sagan was advocating, sending messages on Pioneers and Voyager spacecraft, sending messages about, containing who we are, what we do, and how friendly we are. And so basically that's something we can do now on a very different scale.
Is he who advocated for putting the map on Voyager?
Yes.
Okay.
Yes. So
Yeah.
yes, exactly. So in the spirit of Carl Sagan's idea, we can use this solar sailing spacecraft. He actually was a very vivid advocate for solar sailing as well. And so now we have the technology that actually will be able to implement his vision, but not only in the solar system and, moving very slow, but now we can take this to much distant, destinations. And that can be done. So with solar sailing, what is needed is a low mass spacecraft and large area for the sail. And also the sail has to survive thermal environment when it goes by the sun.
Hold on. Why does mass matter if we're in space?
Because acceleration that you can get, the force that you get from the solar radiation pressure, is inversely proportional to the mass and proportional to the area of the spacecraft. The larger the area, then basically, it's acceleration that you get. It's area to mass ratio.
Yes.
So the larger for a given mass, you need to have a larger area, or for a given area, you need to have a smaller mass to get faster acceleration.
Okay.
And so this is why small spacecraft and the large area of the sail can allow you to actually get very high velocities. And the materials that are needed to survive very close solar proximity are now available. So we can routinely reach distances of, let's say, quarter of astronomical unit. So at some point we'll be able to reach distances proximity to the sun, like maybe 20, 25 solar radii, without being, burnt. It's
Yeah.
very close.
Yeah.
So thermal environment is very predictable, and going there, we know how to do this. Potentially, we can reach velocities, just extremely, extremely fast velocities that will allow us to explore solar system, not within the lifetime of a scientist, but basically many times within the life of a scientist. Because now, once we build a mission, when fresh graduates of who are interested in doing planetary physics, when they graduate from universities, they get in on the proposal team, to propose a mission, and then it takes maybe several attempts to propose. Maybe in 10 to 15 years, this proposal is funded. Then it takes another maybe 5 to 10 years to develop a mission and then fly in it. And it takes another maybe 10 years of flight before the science data is collected. So we're talking about maybe a couple of decades in the mission development. This time should be shorter, and with solar sailing, we just can do that.
Let's talk about your proposal for gravitational lensing, and then let's talk about gravitational lensing. How did you go about the proposal? What was the genesis of this, and what was your realization to start it?
Realization, there is a problem. And this problem, let me express this in a positive way. Remember yourself being a child when you're 6 or 8 years old. You go at night and you lay on the ground on the grass and you look at the stars.
Yeah.
And you look at the stars, and those twinkles, twinkly, twinkly little stars, they kind of bring our imagination, and we start asking ourselves, are we alone? Are there aliens? Are there some, intelligent life out there? And until recently, those questions were pretty much, in the dreams of humanity. You can look in literature for the last, maybe a couple thousand years, literature in different, manuscripts, and you realize that people dreamed about life being ever present in the universe. But only recently, about 20 years ago, we start getting a very solid confirmation that indeed planets are not single accidents. Planets are ubiquitous. The planets orbit pretty much every star in our galaxy. I would say maybe 50% of stars in our galaxy have planets. And so we're talking about potentially about trillion planets in our galaxy alone. Okay. And so by now, by November 2021, we are able to discover about 4,500 planets in our stellar neighborhood. Okay. Those planets are rather big Jupiters because our techniques are very sensitive to larger planets. We are not yet discovering planets similar to our Earth, or at least we have not discovered many of them, only a handful.
Right.
And we are looking for those planets that will be orbiting their star in the distance where water may exist in 3 states. So liquid, gas, and solid, right? And so if water may be in 3 states, we think that there may be some organic life. So we call this area like habitable zone. And so once we start discovering those planets in a habitable zone, then the question will be even more important. Are there life? Is there a contemporary life to us? So we will be able to start looking at those planets and be able to explore them. But the challenge is that those planets are far and they're very small. So, for example, our own Earth is about 115 times smaller than the Sun in size. And so it's very light and very hard to see that object on the background of the Sun. Because to discover exoplanets, imagine you have a strong searchlight, such as, like a strong searchlight, and you have a firefly that flies around that searchlight. It's very hard to see a firefly on the background of a searchlight because searchlight dominates.
Yeah.
And so because planets do not emit light, they reflect light. So it's very difficult to see those tiny fireflies orbiting the searchlights. And so there are plenty of techniques developed, but still most of them are sensitive to giant planets. And if I want to be able to see our own Earth orbiting the sun at 100 light years away, I need to have access to a very large telescope. The diameter of my telescope should be about 90 kilometers. And as you know, on the Earth, we were able to build ever larger telescopes. And now we are waiting for completion of something called European Extremely Large Telescope that will be commissioned next year in Chile. It is 39 meters. It is a segmented mirror with adaptive optics. It's 39 meters on the ground. And I just mentioned 90 kilometers is needed to resolve an exo-Earth at 100 light years away. So there is no way we can actually build anything on Earth that will resemble that telescope. So without some unique capabilities, technologically, humanity will not be able to build an instrument that will be able to see the life on those exoplanets. So therefore, we start looking for something exotic. And of course, general theory of relativity tells us that any massive body may be considered being a lens, because when light travels nearby a massive body, its trajectory is bent. Similar like when light goes through a lens in the optical system. And among the solar system bodies, the sun is the most capable to be used for as a lens because it's most massive, and we know gravitational field of the sun quite well. And when we start looking, we realize that the sun may be used as a giant lens.
Sure, yeah.
So at the distance of roughly 547 astronomical units out from the sun, there is a focal line begins. It's the lens, gravitational lens, does not have a single focal point. It has a semi-infinite focal line. So if I position a spacecraft along that focal line, I don't need to stop. I can move further, just sort of aggressing the solar system. And when I position a spacecraft with a 1 meter telescope that has a coronagraph, the instrument that can that blocks the solar light, I will be able to use the sun as a very interesting magnifying glass that provides light amplification on the order of 100 billion times. It's 10 to the 11th.
Okay.
It provides me with a very interesting angular resolution, which I cannot obtain by other means. It's like 0.1 nanosecond. That means with this type of resolution, I would be able to see not just the width of a human hair on the moon. I'm sitting here on Earth, and human hair on the moon, not only width of the human hair, I will be able to resolve the human hair by, I think, 10,000 times. 10,000 pixels width of the human hair on the moon. So that's what the gravitational lens of the sun gives us.
Yeah.
When we start looking at this, we realize that we can use the sun to actually build, to come up, to develop an image of very distant objects. Direct imaging, high resolution imaging, resolved imaging. So we can think about, for that exoplanet that I mentioned, we take our own Earth, we put it at 100 light years away. With a 1 meter telescope, I will be able to see this object with about 1,000 pixels across, 1,000 by 1,000 pixels.
Okay.
And so that means I will see continental lines, weather pattern, topography, and a lot of interesting features. So suddenly the question about are we alone comes into the practical venue. So physically, we don't see any showstopper to use the sun as a gravitational lens, but engineering problems are quite challenging, and I think we have a very solid idea how actually to address those engineering problems. And the biggest problem is actually to get there in a reasonable time, because it's rather fast. If the lens would be, if the focal region for the solar gravitational lens would be closer, we will be there tomorrow. But at this moment, it's solar sailing is our only way to get there.
Einstein brought this up after his theory, after he obviously created his theory, right? He actually, this exact application, correct?
Einstein actually calculated light deflection, and while studying a suggestion by some scientists in 1936, the general theory of relativity was proposed. by Einstein in 1915. And before that, he computed several effects, but not light deflection. Later on, he studied gravitational lensing as a potential as a potential to use for amplifying light. I believe he actually studied gravitational lensing. He suggested a number of effects, but he was not concerned about using gravitational lensing for some practical purposes. I think it was von Eshelman, who was professor at Stanford University. He was the principal investigator on a radio science experiment in Voyager 1, who actually suggested that we can use solar gravitational lens as a means to communicate with alien civilizations using radio waves. And he actually computed the first sort of first steps of using that lens for that purpose. But later on, we realized that we built a very elaborate wave optical theory to explain this phenomena. Actually, now able to compute all the relevant quantities and estimate signal to noise ratio, all the important parameters that are needed to use the lens in a practical manner. So our group now is actually quite confident that a mission like that will, to the solar gravitational lens, will allow us to see distant worlds with very high resolution, but not only see, but also to do spectroscopic research of those targets. Spectroscopy will tell us whether or not this object has oxygen, nitrogen, methane, and so those sort of gases that actually suggest the presence of ongoing life. So yes, Einstein himself studied the gravitational lensing, but he did not actually look at this as in a practical manner, because back then not many people actually were excited about taking even to measure this effect. I think it was Adjunct who in 1919 was the first person to conduct experiments studying gravitational deflection of light. And so Eddington confirmed that indeed general theory of relativity is a valid approach, but that was just within a geometric optics approximation where you can just study that indeed gravity deflects light, but not in any practical meaning. So now we have the technology and we have the means to actually develop solar gravitational lens as a component of a giant telescope that humanity will be able to build in the near future.
And we can also use this, if this is indeed the universal tool best used to observe, we can surmise that maybe at other convergence lines and other star systems there are craft to look for. Have you thought of that?
Absolutely. We can use this as a communication channel. So we can communicate between the two civilizations. You can imagine that in the same focal region of the solar gravitational lens, instead of putting a receiver optical telescope, I can put it in transmitter. And transmitter may be high power laser or other types of transmitter. And I can send the light back and using the gravitational lens in reverse. And that can be done. And we can communicate with the similar system on the other end. So yes, it is possible, and we have done sort of preliminary calculations to suggest that yes, if we have somebody to talk to with advanced civilization, so yes, potentially we can establish very sort of focused communication channel between the two civilizations.
And what does your gut tell you about life in advance and how advanced possibly out there? From my side, I see three things. I see the general uniformity of the same chemicals all throughout the universe is what we observed so far. I see time, 14.8 billion, and I see, those two things, and I see basically those things. And when you look at those things, in the time of Earth, 4 billion, it took Earth to kind of create us, and then you take 14.8 billion, it's obviously much more, and space itself is the third thing. That, I mean, tons of space is available and tons of star systems, and as you said, 1 trillion exoplanets just in this galaxy. It seems to me it's obvious that there would be, based off of those three parameters, even more intelligent life. That's so. Do you want to prove me wrong in some sense, or do you agree with that?
I totally agree with you, and yeah, this is why I like talking with you. You're an optimist, and this is nice. But when you put realistic numbers, you start thinking about what conditions around the star may support life. So you can immediately exclude the inner part of the galaxy because the radiation from the center of the galaxy is quite strong. So you understand that when you have a strong radiation, organics do not like being irradiated quite strongly. So potential life may exist in kind of a around a boring system where the orbits are very circularized, so that if the orbits of planets around a certain star are still elliptical, you cannot allow for such a variation. So astronomy plays a significant role. Why variations are bad? Because imagine if the orbit of our planet would be elliptical. So some part of the year temperature will be below freezing, very much below freezing, and some part of the year there will be very hot because through the year, our planet will be either at a very close proximity to the sun, because the orbit will be elliptical, or will be very far. So the temperature on the planet will be very different between different parts of the year. So the fact that the orbit of our Earth is pretty much circular, we can, as a result, the temperature on our planet is varies through season to season, but not significantly. So imagine if the orbit will be, if the planet, if Earth would be orbiting on the distance of the Venus orbit, so the temperature would be 200 to 285 degrees Celsius.
Yeah.
Life cannot exist on these conditions. Or if Earth would be on orbit of Mars, temperature will be very cold. So life, as we know it, will not exist there either.
As
So
we know it. As we know it.
exactly.
Yeah.
So organic life, we are looking for life that resembles us because
Right.
this is what we understand the best. And in reality, our Earth is in such an ideal orbit such that it doesn't vary too much. And actually, this is why we are being developed this way. We need to have a very stable orbit so that it will take many years of genetic evolution for us to evolve from one species to another. For the last 70,000 years, our ancestors went from being primates, and now you and I talking through a Zoom through a telecommunication channel, right? And you can see how back 70,000 years, our ancestors were roaming savannas in Africa, and so there were 5 different species of sapiens, and so only Homo sapiens became sort of advanced. There were Neanderthals, there were Denisovans, but for us, abstract thinking created the opportunity to evolve. So you and I are here because our ancestors started to develop something called abstract thinking, where we can disconnect ourselves from reality and move on and start to develop something that is reality that lives only in our consciousness. And so that is a complex development that was provided by the conditions on the planet Earth, because we need to have a very stable environment so that our genetic composition, our structure, and our life will evolve. If we would have to fight with the environment, it will not be a very comfortable environment for us to evolve. So what I'm saying is that even the astronomy influences life quite in a drastic way. For example, if our planet will be smaller, so you and me would be probably smaller in size because the gravity field of that planet would be, will dictate that the amount of oxygen that we need would be smaller. So the heart would be smaller, so it will be pumping blood, but then providing us with enough oxygen. We don't need to have body like big body in a smaller gravity environment.
Yeah.
Instead, when we live, if you were to develop in the stronger gravitational field, if the planet would be larger, so we need to have a much bigger heart to be able to pump blood to our brain. So the planet, its orbit, and the amount of thermal energy that we receive from our sun influence biology and influence the development of us
And
as humans.
the tilt as well.
Absolutely, the day and sort of the seasons and the days, and the fact that night and day are strongly influence on our psychology and physiology. So we need to get rest, we need to wake up and be active, and then we need to get rest again. So basically, it's all the adaptation to the environment that we were given. And in reality, we speak because we have atmosphere. We can walk because it's more advantageous for us to walk. So it's all the adaptation to the environment. In my mind, I think life actually may have some primordial code, and so that code it's basically can account for a number of different conditions. For example, if that code would be deployed on a planet with different environment, different parts of that code would be activated because they will be adopted to that particular environment. And some of them will be dormant because there is not enough energy to activate that particular part of the genetic code.
So it sounds like you're a proponent, or you kind of believe in panspermia.
Panspermia, maybe it's panspermia, but maybe life is something that is traveling through the galaxy. It may started somewhere, and then it may be evolving through, by traveling through the universe, through the galaxy. Panspermia is one thing, but maybe it's after all, organics is the chemistry. So chemical elements are abundant in the universe. So basically, you and I built from the stardust. And so that stardust, under certain conditions, forming us the way we are, basically using the same chemical elements. But maybe there is some additional components that we are yet to understand how life may actually evolve under certain chemical and chemical conditions when the energy is abundant, when when appropriate components are present. Maybe this is where life will just form on in this particular environment. So life may be an integral part of the evolution of a chemical system. We don't know what life is, reality, but you and I now sort of theoretizing. But potentially it's either panspermia or maybe just an integral part of evolution from early bombardment of the primordial Earth, then evolving some kind of very very bad atmosphere, then big animals, the oxygen, nitrogen appears, the plants, and ultimately intelligent life is part of the natural process that begins with the forming planet and forming the ecosystem. And yes, those questions that we discuss now, it's kind of part of the theoretical discussion. Yeah. And when we talk to astrobiologists, they're people who are very focused on the environments that they will understand. We now look back at Earth, how Earth was prebiotic conditions. The atmosphere was different. The oxygen percentage of oxygen and nitrogen in the atmosphere were quite different, not consistent with life at all. And as plants and humans started roaming, as humans started roaming the planet, the atmosphere changed, and now we are changing the atmosphere of this planet yet again with global warming. So coming back to your question, life on our Earth evolved on its own time scales, but life on the different planet elsewhere in the galaxy may be evolving on its own time scales. So it's not guaranteed that we will be contemporary. So you and I may be sitting here today, but that conversation may not happen on the other planet or already happened in the past. So basically, we will be lucky if in our neighborhood we'll find a civilization that is still active. It's still active and still ongoing. So it's although I am optimist, the way you posed that question, and I agreed with you. Yes, life is somewhere out there, but there are many factors influencing whether or not this life already is a contemporary to ours, or may already sort of existed on that planet and ceased to exist because the star went through a very boring, nice, comfortable star as our sun, but then exploded and basically swallowed the planet. Things may go very drastic in different ways, and so it's we are happy here. I guess we have to be thankful to what we have today. We live, we breathe, we look forward to to a productive life, and this is wonderful. So, but yet our civilization is now pressed with many interesting questions because technologically we are able not only being driven to sort of looking for life in the universe, but now we have the technology that actually will help us to look for that life.
Yeah.
And so only a couple of days ago, there was a report from National Academy of Sciences relevant to discussing the priorities for the next decade in exoplanet research, for example. It was Astro 2020 report that actually is astrophysics, covering all areas of astrophysics, recommending NASA to do certain programs. And one of them, of course, looking for life, looking for biosignatures. We are not yet confident that we will find life today, but we are looking for exoplanets that may have conditions consistent with life, potentially inhabited. So we are very carefully phrasing that, because technology that we have today is not yet there. Maybe ultimately we need solar gravitational lens to observe life as it is on the other planet. But we are we actually developing all the necessary tools to get there.
Yeah, I can't imagine any other way to actually do that, to look as far and with the resolution that you mentioned. And when we look at when we take spectroscopic information from these planets, I'm assuming when you talk to the planetary scientists, when evaluating what planets to pick, you're talking about oxygen. Is that the main thing we're going to want to look for?
Oxygen, nitrogen, methane. We're looking for those swamps because swamps, release a lot of methane, and so methane is actually it's a gas that indicates that there are ongoing organic biological processes on the planet. So we are not looking for just static environment where oxygen and nitrogen exist, but methane is actually it's an indication that ongoing disturbance in the ecological system. So where swamps, where maybe cows are roaming the planet, so it's something that actually indicates the presence of ongoing life.
Should we bring Venus then? How do you feel about the Venus thing a year ago?
Too close to its to the sun, and it's pretty hot. There may be some molecules we'll find in the atmosphere of Venus, but on the surface, I don't think so. Going back to the Soviet Union program, I remember being in the flight control center when the Venus lander was going to land on Mars or on Venus, right? And so, of course, the temperature was the main sort of instrument. So the thermometer was the main instrument that we were looking at the time, and anticipating that temperature would be reasonable. As the spacecraft would enter the atmosphere of Venus, it started going down. Temperature was 20 degrees Celsius, nice. Then it would be like 40 degrees Celsius, still okay. Then it was 120, and people faces lost smiles. Then it was 200 degrees Celsius, and reality is that Venus is pretty much pristine environment with no life.
Okay.
And so we don't want to have anything like that. We really want to have find a planet where thermal environment will be very close to what we have here on Earth.
Yeah.
But nobody, it's not guaranteed that life may be only, in the forms that you and I know. There may be some other different forms of life, and but we know very little about those forms.
Yeah, I mean, we evolved, and everything that exists on planet Earth evolved to live on Earth. So we have to keep in mind the things that you mentioned with how small it is and the tilt and all that stuff. And we can actually take all that data and do simulations one day maybe, and create a 3D model of a life form that might be on an Earth, on a planet based off of those things you said.
And we do that, and we have all those simulations, because those simulations are important. They inform our ability to search for certain signatures, because the current techniques that we have are looking not even at one pixel, because we cannot resolve those planets with one pixel. We look at a light blob that we detect. Like direct imaging technique allows us to search for exoplanets that are quite large. So we have like a light sort of spot. And with this one spot, we can try to do some spectroscopy and understand what conditions in the atmosphere of that exoplanet might be. And but for that, we need to start from modeling that exoplanet as it has all the elaborate life forms on the planet, and see how that will be integrated into one single pixel in a sense. And so yes, we have those models developed, and there are quite a few members of the community that actually developed those elaborate models. We have several of them. We use data on our own Earth provided by Discover spacecraft that is monitoring Earth at real time, and we develop models that allow us to model seasons, to model chemical composition of the atmosphere, to interaction ocean and the land, the ice caps, all the wind flows and the global atmospheric circulation. So we need to, and the water circulation. So we need to be able to model all the hydrodynamic conditions, the thermal conditions on our own Earth, for us to understand, do we really understand Earth? Do we really understand life on our planet? Before we embark on studying other planets, we need to understand how life formed here and how it's being supported here by the environment that we live in. And then when I guess it will be interesting for us to see those exoplanets, and that will tell us whether or not those aliens who live on those exoplanets are ruining their environment as we are, or they are more careful compared to sort of the carbon, the using the fossil fuels. So are they ruining their planets as we do, or they are smarter than us? It will be interesting to us.
That might be an element in the great filter, and if they got past that, then that's hope for us.
Yes, absolutely, and I think now as technology evolves quite rapidly, we need to be able to process this technologically provided insight. If you go back to 200 years, back then, I guess technology, most of the technology that we deployed on this planet was related to agriculture. So we would be planting seeds, would be collecting seeds and raising stock animals and sort of consuming all of the proceeds. That was our basis of economy. Then steam engines and came about, big factories, then trains, then planes, then we have lots of boats developed. So technology for the last 100 years evolving rapidly, and especially for the last 20 years, because now we are entering digital age, right? So everything is now digitized, and so we're moving forward by relying on digital information technology in the biotech. So I guess somehow the symbiosis between information technology and biotech will help us to develop the new drugs to treat the sicknesses and support our life. We will live longer and healthier. And so lifespan increased significantly for the last, 60 years even, because we now are able to treat the diseases and able to provide environment, understand what actually influences life. Well, what I'm saying is that as a species, I think genetically we did not change that much, but technology and lifestyle changed significantly. If we project this development, let's say to 50 years in the future, technology that we possess today will evolve exponentially. It's very hard to predict actually how it will evolve, because can you imagine predicting a video conversation, let's say maybe 20 years ago? because back then it was just you go, that there would be sort of a telephone on the street, you call people, and this is it. You probably don't remember that, but I would be, I would call my friends and parents from Pasadena, California, calling back to Soviet Union, right? So the phone, I would see, it would be extremely expensive. Now we take Zoom calls; they're pretty much for free, right? So technology affects our daily life, our communities. What will happen in the next 20 years? It's even more because now we are driven towards the sort of our social networks and our telephones and sort of platforms that we use. Information access to information is pretty much instant. So whatever in the past differentiated different people was the muscle power, and so now we still have the muscle power and ability for the sports, but now I guess the most the best quote unquote muscle that we need to develop is our brain.
Yeah.
And so humanity needs to spend more time into education and developing the brain conditions and improving the sort of the most cherished part of our body, which is brain, the intellect, support that. And so I trust that our society will evolve quite rapidly in the next 50 years. And thinking about what life on this planet will be within 50 years, it's now we go exponential growth.
Right.
And that will be quite interesting because when we think about meeting aliens or looking at exoplanets, they probably underwent similar development, exponential technologically infused development of their species. Maybe I'm not even talking about artificial limbs and a sort of merger of human and robots and basically androids. That's a very different topic, right? But potentially you can see that there may be some synergy between biotech and sort of in the IT that will create a different human beings, sort of human 2.0, right? And so how do we deal with artificial intelligence? How do we deal with all the robotics that is now thriving and so many exciting robots are being developed? So who we are as a species, how do we manage our life among those different, androids that are being deployed as we speak? So this is very exciting.
How are you guys and NASA thinking about autonomy? We talked about this a little bit before, but
autonomy is critical.
Yeah.
For me, when I talk about solar gravitational emission to the solar gravitational lens, autonomy is the key because the one it's round trip flight time is about 7 days. So I'm sending a command today. It takes about 3.5 days to reach my spacecraft, or maybe 4 days one way. And so I cannot expect myself to navigate that spacecraft in real time, right? So I have to trust my spacecraft. I have to cut umbilical and so let it go because this is the only way to actually explore distant worlds, to trust the system that it will be able to recover from a fault, to be able to collect new data, to process and actually communicate back the results. Even today, when we fly our spacecraft to Mars, when we land on Mars, there is those famous 8 minutes of terror because when spacecraft enters Martian atmosphere, you cannot expect to navigate it anymore because basically the signal, it takes almost 16 minutes for the signal from Earth to Mars to reach the spacecraft. It's a one-way signal transmission, 16 minutes. So by the time you try to influence the course of your spacecraft, it's landed already, right? So basically you have to develop everything so that spacecraft will be completely autonomous into determining the most optimal flight path to survive during landing.
Where it needs to scale with hardware if we're going
to absolutely. It has to be done this way. It's not yet fully what is intelligent system because you provide it with the decision tree. Yeah. And so essentially when a spacecraft encounters this atmospheric airflow, or maybe it sees a rock on the landing site, it has to implement avoiding maneuvers. So it has to have enough sensors and enough computer power on board to execute two to see the obstacle and to be able to avoid that obstacle and compensate for any failure during entry, descent, and landing. So this is one example. Another example, when SpaceX is landing their boosters, right, the first stage boosters. Imagine landing a pencil. You take a pencil and you land the pencil on its head, right?
Yeah.
So this is not very stable system, but yet we start seeing, and we are now asking question why nobody else does it. So it looks like almost effortlessly, but you can imagine how many computations onboard computers are doing during descent. So the system is totally autonomous, but it's not yet intelligent. So there is again decision tree.
Yeah.
So there is a difference between sort of full intelligence, artificial intelligence on board of a spacecraft, and full autonomy. For now, we're talking about autonomy, which implies that, yes, we have thought about everything that we know about the environment spacecraft will be traveling through, and we provide enough enough solutions for spacecraft to choose from, and maybe pick the best optimal solution among the sort of all the possibilities. So that's how we develop autonomy for the spacecraft. But yes, indeed, this is a must.
Yeah, with convolutional neural networks, I think we'll get past full autonomy, and then we'll get to decision making based off of just our initial input. Go do this, and then it'll take all the information in, vision, hearing, all of it, just like we do, and just do it. I think that's it's a few years out still, but I mean, we'll get there, and I'm sure before we're able to send the gravitational lens out.
Absolutely. And see, I think in the past it was limited by the onboard processing power, onboard processing capabilities. Now we can talk about very fast processors on board of a spacecraft. They may be qualified for flight, and when you can do most of those calculations on board very effectively, and a lot of flops being processed. And so essentially, you can now trust your spacecraft to do all those calculations in flight. You don't need to get the signal back to process it and then upload the command. So you can now rely on your spacecraft because it has enough power, it has enough, processing capabilities on board, and therefore you can actually, you can deploy the autonomy to the spacecraft completely. And you're right, we are now evaluating a lot of different applications of these autonomous systems.
Yeah, Moore's law is going to yield something in the time it takes for us to get at the convergence line, I think. So that's going to be
absolutely
exponential from what we have today. And so let's be really optimistic. Let's say we do launch this, it goes really well. We look at our first planet and it's a hit right away, and we see spaceships flying in the atmosphere of that planet. What do we do next?
At that time, I don't think we'll do anything drastically, because at this time, even our technology will not be, I think, even taking the technology evolution, I don't think within the next 150 to 200 years, humanity will be able to travel interstellarly. And maybe we don't have to travel interstellarly. Maybe we have to let androids to do that. Yeah. So, but realistically, to travel to the exoplanet that we just observed, it may not be feasible technologically, but still establish communication and monitor and learn. It will be very exciting. It will be first ever contact. I think it will be transformational change for the humanity, because now we are not alone, and there is some sister civilization that is out there that can be used as we will try to establish communication. We'll try to observe first, and then see at what stage the civilization is. And I think immediately we will deploy more resources to observe that system.
Unfortunately, we're again confined in a bad way by space-time, and that, I mean, we'll probably be looking thousands, millions years in the past when we see that.
It depends on the distance to that system. If that system is within, let's say, 50 light years away, so we're looking only 50 years in the past.
Oh, okay. So there are exoplanets that close.
The exoplanets were discovered in our stellar neighborhood within 15 light years. So 1.5. And so there may be some exoplanets discovered even closer. So maybe the Alpha Centauri, the Proxima b and the Alpha Centauri system may have planets that may bear life. So this is our immediate stellar neighbor. It's only 4.3 light years away. So potentially we may discover exoplanet orbit in that system. So that will be complete neighbor. And but within 10 light years, I do expect there will be plenty more systems similar to ours. And so it's a matter of deploying enough resources, enough telescopic assets to look for those systems. And within 100 light years from us, definitely there will be plenty of systems. And so the environment is our immediate neighborhood, a stellar neighborhood, will be pretty populated with planets.
Do you have a single planet in mind? Because obviously we need to pick the planet first before we go. So
at this time, we have only systems that don't yet have, Earth-like exoplanets in the habitable zone. We don't yet this, planet that actually we would definitely go. But maybe one of the systems that we probably would like to look at is TRAPPIST, because it has multiple systems, multiple planets. And we may go to explore TRAPPIST and see all of those planets and understand conditions on those planets. And so with the solar gravitational lens, we are not looking just at one exoplanet. We are looking at the entire planetary system that is formed around the star. So potentially when we look, let's say, looking at the solar system, we can explore every planet orbiting the sun. And so this is the benefit of the SGL. But we cannot, with the current technology, with the current propulsion technology, we cannot repoint our telescope to a different stellar system. So if there is another sun with the planets, we cannot use the same telescope because it will require significant propulsion capability on board to move laterally. And so if our mission turns out to be affordable, and that's what we hope for, so our current analysis shows that the mission to the solar gravitational lens will be very affordable, meaning will be on a scale of typical mission going to Jupiter or Mars, so which we can afford these days. And so in this case, we can fly several missions to look for the high value targets, in a sense. If we identify a list of high value targets where we see confirmation of different gases, confirmation of the fact that the planet orbits in a very appropriate distance from its host star, yes, why don't deploy several missions like this? And so with the solar saline technology, the mission is actually affordable. And as you know, there are two most abundant elements in the universe. And so those elements are non-existentium and unobtainium. And so recently I discovered the third element, which we have to put in addition to this two. It's non-affordium. Right. And so reality is that the mission to the solar gravity lens is none of the above. So it's actually feasible, we can make it, and actually it's affordable. And that's a very different story compared to when we began studying this mission. So it's a challenge now to actually build something that's called public-private partnership, where not only NASA and federal agencies will step in, but maybe also private industry, where private industry will be able to develop pieces of technology for commercial use. And we have several of those technologies that now private industry is interested to step in and to develop them for commercial use. For example, solar sailing technology. You can sail and deliver in packages, and maybe remove debris around Earth. So those technologies will be developed within the public-private partnership. And ultimately, we are hoping to fly in about 12 years from now.
Okay.
And so it's a very challenging environment. But by the year maybe to 2036, we would like to deploy first a mission to the solar gravitational lens focal area to study a very interesting exoplanet that will be discovered in the next couple years. Test mission is flying now, then we expect to have James Webb telescope and then extremely large telescope on the ground. So we are looking forward to have a handful of very high value targets in the very near future.
And besides planets, have you guys talked about looking at other cosmological bodies that are interesting, like black holes and We have a lot to learn about that stuff. Honestly.
Absolutely. And quasars. They are supermassive black holes that are situated at the very edge of our universe. So
Okay.
they're situated roughly at the distance 12.4 billion years from us. And
Really?
usually we use quasars as point sources because they don't really move from the sky. They're so far.
Why are they only at that distance?
Because they were formed very early in the universe, and they're very sort of a supermassive black hole that was born at that very early stage of universe, and it's surrounded by a number of stars and galaxies there. So we don't know much of them, but we know it's a very massive object. And so they're point masses, they're point sources, and we use those quasars for navigation. When we fly a spacecraft to Mars, we have something called what is 267 reference quasars. When we know their position on the sky, and we can navigate our spacecraft with respect to the position of those objects because they're very well studied. But we've never thought about actually making pictures of those objects. With the solar gravitational lens, we are talking about resolving those objects from point source to roughly an image of about 600 meters. So you can now study how the black hole is actually formed there, what is accretion disk, and how where the radiation that emitted by that black hole begins.
Hawking
And so you
radiation.
can absolutely not Hawking radiation. Hawking radiation is slightly different, but basically when you have accretion of matter on that black hole, the matter is orbiting and forming the disk around that black hole. You will see where a lot of interesting processes are happening. So when matter starts infalling and radiating as it falls into the black hole, so those processes are only theoretically predicted, and so we can now actually confirm or disprove the history or physics of those supermassive black holes, which is quite exciting. So potentially we can fly solar gravitational lens today if community decides that observing those supermassive black holes will be of significant value. And so far, with the images from Einstein Horizon Telescope providing images of black holes, we can actually improve those images quite a bit. So we can zoom in inside the close to the event horizon. And that is something that no radio telescope will ever be able to do with optical and maybe X-ray technologies. I mean, with the X-ray technologies are heavy to fly because they require significant infrastructure, but maybe optical techniques and infrared will allow us to get a very exciting information about supermassive black holes that are at the origin of the quasars. And so that's one example. Studying black holes, definitely. Looking at the sort of neutron stars orbiting each other, we can actually see what is happening in the super intense gravitational field around, neutron stars or black holes. So this is where solar gravitational lens is a unique instrument that will allow us to observe those unique sort of regions in the universe.
And for the SGL, the physics you mentioned is pretty much done. It's now on engineering, or maybe 90% done with the physics.
We have developed the critical component of the physical insight studying solar gravitational lens, and that is we now have wave optical treatment of the lens, which is allowing us to treat photons not as particles but rather waves. And so that is very important for the optics of the system, for the optical systems. We can now use the same techniques that were developed for to study optics for the last 60 years, and use the same technique to design the optical instruments that will be actually built around the solar gravitational lens for imaging. So wave optical treatment is unique. So we have that done. In addition, we now treat the sun not as a point mass, not as a monopole, but actually the sun is oblate. And the sun is not spherical symmetry because it rotates, it has some oblateness. And so we now are able to integrate that ablateness into the model. So we now will have a very elaborate physical model of the solar gravitational lens. And so with this, we pretty much completed the theory that is supporting this interesting phenomenon. Now we are moving into engineering efforts because we need to study and identify what is the telescope diameter will be for the most optimal observations. If it's 1 meter, maybe 2 meter telescope, so that we want to build image quite rapidly, so that we do not wait many years to make first image. Because realistically, we would like to be able to compensate for the rotation of the exoplanet, because exoplanet rotates and not only orbits its own star, but also rotates. So this way, we can actually remove the cloud cover and peek on the look at the surface of the exoplanet. This is what is ongoing right now. We're conducting many simulations to study the imaging capabilities of the SGL to identify the most appropriate instrumental parameters. So we have, go ahead.
I was just going to say, are some exoplanets in retrograde?
They may be. It's basically the orientation of the orbital motion. It's completely not connected to our planets in the solar system.
Because if some are retrograde, then we're going to be looking at the dark side of the planet, and then we'll get no data. Correct?
It depends how we look at how the stellar system is oriented with respect to our direction of the way we look at them. So it may be that the exoplanet may be transiting. That means that exoplanet may go through the disk of its own star. So when it comes to that, when it starts to approach its own star, we will not be able to see it, because it will go behind the. It will be affected by the background light of the host star.
Yeah.
But if it's further away, we can observe it. But at this time, it's not a fully illuminated disk. It's only like a crescent of the moon, right?
Yeah.
And so we will be observing those crescents of the exoplanet, and the crescent actually is rotating, right? Because we see it as a crescent, but what forms the crescent is rotates. So we need to be able to treat this motion and to be able to observe it. So yes, there will be some dark part of the exoplanet, but some crescent, depending on the orbital phase, will be either smaller or larger, but it will never be, I guess, in full illumination. It will be only half of that. Mm-hmm.
Yeah, will these be 2D models or 3D models that we're able to yield from this?
We will use 3D models ultimately, because 3D model is very is capable to explain how the image is projected on the image plane. So ultimately, we have to translate this into three-dimensional model of the exoplanet. So yes, ultimate model will be three-dimensional. At this time, in our simulations, we use two-dimensional projections, and that is sufficient for the purposes of this study. But ultimately, when we will get the data, we'll have to develop three-dimensional models of the exoplanet to identify where that mountain, which has the ice cap, and where that swamp on that exoplanet, which has the methane emission, or where the boundary between the continents and the oceans is. Are there some lakes, rivers on that exoplanet? So we have to be able to correlate the data with the three-dimensional structure of that object.
And I just realized an obvious thing. Will you be interested in looking for synthetic objects in orbit of these planets?
They will be smaller in size, and resolution probably will not be very good. But as we look longer at the same object, right? As we look maybe for a few years, we should be able to identify the presence of those artificial objects. Any orbiter, maybe moons. Definitely, we will see the moons. We will definitely see the moon. Absolutely, the moon will be resolved by many pixels.
Okay.
But using artificial satellites, they will be too close to the, let's say, to the exa-Earth. And so depending on, to see an International Space Station probably will be difficult. Maybe once it provides sort of the what is when it reflects light from the exosun, so to speak, when we have the light reflection, when it will be amplified, probably we'll see some instances where space station, exospace station, will be reflecting light towards us. So those events we'll definitely see.
And of course, terrestrial lights as well.
Absolutely, absolutely. When they turn light for the night, we will see those cities at night.
Wow.
Absolutely.
Wow. That would be amazing. So are you guys utilizing AI to take the Einstein rings and patch together that 3D model?
At this time, we don't need AI. We are trying to explore all the venues with the knowledge that we have. So we don't yet go into even statistical assumptions on the different sort of imaging. I mean, at this moment, we don't use AI. At some point, we will use AI because there will be plenty of data. But for now, we use just a regular type of simulations that we conduct using some assumptions on the parameters and the distributions and the image, so the noise properties, all of the important assumptions on the signal and noise properties. Yes, we use that, but we are not using yet artificial intelligence. We would like to explore the available techniques that we can do with sort of decision tree approach. And then ultimately, when the mission will be flown, we will have to integrate artificial intelligence as well. But then, what is the artificial intelligence in this case? We need to be asking ourselves a very good question. So, what is the sample of data that the computer on board need to learn from, right? And need to extract patterns. And potentially there will be a lot of information for the computer to go through and establish the patterns. Ultimately, yes, we will use it, but for now we just don't have a need for this yet.
Gotcha. And what are the odds we can know more about gravitational wave astronomy and dark matter and things that we are on the cusp of learning about from the SGL?
From the SGL, you're asking about different question. It's gravitational wave astronomy, right? It's not gravitational lensing, but yes, we can actually amplify gravitational waves as well. But that's a very different topic. So potentially we can look at the gravity amplifies gravity, and there are some papers out there that actually use amplified gravitational wave signal by the components of the binary itself. And so there will be a perturbation or variation on top of the detected signal coming from the amplified gravitational waves by one of the neutron stars, right? So the similar effect may be used to amplify, gravitational waves that are coming to the sun. But then we need to have a very different detector. We have not looked at this. In my mind, if a mission to the solar gravitational lens will fly, it has to have a very strong, scientifically appealing objective.
Yeah.
And so for now, I think a direct imaging of exoplanets is a strong enough objective for us to work on, so almost exclusively. The secondary science objectives that we discussed, the quasars and maybe gravitational waves, they're exciting. And also maybe detecting neutrinos, amplifying neutrino flux. So those are very exciting as well. But at this moment, I think they will require a very different instrumentation set. For example, to detect neutrino, you need to have a rather heavy neutrino detectors. Flying them to those distances may not be that advantageous. Or X-ray, amplification of X-ray will also require a very different detector technology. And so optical telescopes are most convenient instrument to fly because they may be made lightweight, and they are very reliable instruments. So for now, we are focusing on the optical astronomy in a sense, using optical telescopes. And for that, exoplanets are the most appropriate target to investigate. But I wouldn't mind to bring other objectives into the study. It will have an impact on the set of instruments that we will fly, and therefore the mass of the spacecraft. And remember, we said area to mass ratio. We are very careful to minimize mass of the instrument only to those that will serve the primary mission objective.
What about dark matter?
Dark matter, with the solar gravitational lens, I think studying dark matter may be a challenging idea because you can study dark matter when you can look at the several sort of separated objects. Meaning, if you have several stars and you see how their position changes as time goes by. So astrometric detection. For that, you need to have maybe optical interferometers. Solar gravitational lens may not be the best technique to study dark matter.
Yeah.
Matter. But there may be other techniques to do that. For example, we can do a very good spectroscopy of the orbit of, if you look at if you're looking at galactic center, if you're looking at the black hole, we can do a very good spectroscopy of the stars that are orbiting galactic center. And so this way we can identify very precisely the velocities of those objects, improve velocity determination. And that measurement alone will allow us to prove whether or not significant fraction of dark matter is around the supermassive black hole in the middle of our galaxy. So that's kind of indirect measurement because we can improve velocity determination of the stars orbiting those supermassive black holes.
Yeah. I asked about dark matter just because it represents. I think it's 1/5 of the matter in the universe is normal matter, and the rest is dark matter, which is ridiculous. So there's tons of theories around that. Are there any that? How do you think about that? Are there any that you prescribe to or are interested in?
It is exciting period of theoretical physics because until probably 1936, we knew that we pretty much cover all of the interactions, physical interactions. We know how we can describe physics around us. There were 4 physical interactions: electromagnetic, gravitational, weak and strong nuclear interactions. Back then, especially by the 1960s, it was a renaissance in high energy physics. Basically, back then, a lot of interesting instruments were built in many countries, accelerators, particle accelerators. So that was a renaissance. But there was a puzzle that came from astrophysics, puzzle in the form of dark matter, because Frank Zwicky, he was an astronomer at Caltech, observed a number of spiral galaxies, and he realized that those objects do not obey Newton's law. If you apply directly Newton's law to explain the velocity of the spiral arms, so you take a star within the spiral arm of a spiral galaxy, and you can estimate velocity of that part of the spiral arm as a distance from the center of the spiral galaxy. Newtonian gravity gives you an answer, pretty much straightforward answer. But when you try to match it with observations, you realize that there is a lot of mass missing. And so that mass may be in a very different form of energy that we don't see in the form of electromagnetic energy. Because what we observe in the universe, basically, it's electromagnetic spectrum. Visible, infrared, X-ray, gamma rays, it's all electromagnetic spectrum. But there may be some forms of energy that do not reveal themselves through this electromagnetic spectrum. And therefore, the term of dark matter came about. Because the matter is there, the mass is there, the form of that mass we don't know. But it's there, it's present, and therefore it affects the dynamics of spiral galaxy. And so that was one puzzle. And in 1998, we got another puzzle, which is dark energy. We realized that the universe, after Edwin Hubble, also a professor at Caltech, suggested that universe is expanding, uniformly expanding. After Big Bang, after inflation phase, it's uniformly expanding. And that was just kind of very common model for the universe evolution, for cosmology. But in 1998, we realized that the universe may not be expanding uniformly. Something is pushing the universe from within. So something is pushing it outside, accelerating the expansion. And about 1.5 billion years ago, something happened when the universe started to expand in accelerated fashion. So dark energy came to life.
Yeah.
The puzzle that we faced is to explain why on a larger scales, as opposed to dark matter. Dark matter you revealed on the galactic scales, but when you go into cosmological scales, dealing with the whole universe, you just realize that there is another puzzle that we don't really know how universe is evolving. So it's a dark energy. When you put this in terms of all the energy content in the universe, you realize that we know only 4% of total energy in the universe. All the baryonic matter that we are dealing with on a daily life, it's only 4%. So all the rest are the two puzzles. About 20% would be due to dark matter, and the rest of dark energy. We have no idea what those are. We have a very good set of theories how to explain potentially dark matter. But as time goes by, and we have done a significant research into trying to detect a particle that may be responsible to create something that we see in the form of dark matter, but that particle is still not detected.
Do you think space has a particle?
Say it again?
Do you think space has a particle?
Oh, that's an interesting. Space is a geometry. Space and time is a geometry. So we are thinking about sort of a small, tiny blobs of energy, and those energy, the particle, a wave. So we're looking for this type of explanation. But this energy is there, and we just don't know whether or not this energy is going to be new energy. Whether or not those theories that were suggested to look for a particular particle will satisfy our curiosity. But we ask a very different question, and that question is, can we explain dark matter through gravity modification? Potentially, there may be a gravitational theory that actually may be used to explain those puzzles that we see on galactic scales. Yes, and indeed, there are quite a few theoretical physicists proposed gravity modification theories that actually may be used to explain galactic rotational curves. But the two groups of physicists, one group of physicists that are trying to explain dark matter via new particle, or maybe new sort of yet to be discovered physical interaction, and another is via gravity modification. These two groups of physicists are still arguing which approach is better, and experiment is not helping us to put our bets one or another. So to conclude this sort of competition, the puzzle still exists. With cosmology, the problem is even stronger, because after we received this data, no more from the mission that was flown in the 90s. After we realized that the universe is expanding, there were hundreds of thousands of papers submitted trying to explain what may be the cause for this universe evolution. But the jury's out there. We don't yet know how to actually answer that question. So these two puzzles are very persistent. And now even sort of dark energy is also addressed by gravitational modification. So potentially there may be different theories of gravity, there may be some new interactions, there may be some additional dimensions, there may be some different exotic physics that are at play, especially the early universe, and then basically as the connection, as the strength of gravity relaxes with the age of universe, maybe there's some interaction that pops up that we start witnessing. There are multiple exciting mechanisms, but we don't know at this moment. We really don't know. It's a very puzzling time, because we are trying everything to explain this to different phenomena. Maybe we just need more experiments. But experiments are very difficult to get by, because you need to fly a spacecraft and need to be very careful to ask the question, what do you want to measure? And how well do you want to measure? And so that's something that community is struggling at the moment. And again, referring back to the Astro 2020 report that was recently released, I think we will be looking more at more efforts on the ground-based telescopes, larger telescopes that will be measuring distances to multiple objects in the universe, try to identify the distances to them, because the more precise will be the distance determination between to the different objects in the universe, the more precise will be determination of that puzzle, sort of dark energy. So we have a puzzle, and I think it's most as often happens in physics. You have a puzzle, and there is a period of data accumulation. We try to understand, we try to play with different physical theories. We conduct more experiments and study the phenomena. To maybe it will reveal some pattern, and then there will be some conjecture made that will explain it. Or maybe not. At this moment, we don't know. But this is where, I guess, the question about whether or not our universe alone, or maybe there are some multiple universes, came about. So realistically, there are some even suggestions that explaining our universe in using quantum cosmology, where you imagine yourself observing a quantum foam where universe is being born, another baby universe is being collapsed, sort of died. So there is a burst and annihilation of those baby universes. Some of those baby universes are taken off and started to develop in the adult universes, and some of them being collapsed again. And so that's how you can imagine a sort of the quantum cosmology beginning. And some theorists suggest that that may be a way to explain why we have physical laws the way we have them, because different universes are being born with different densities and set in different physical laws. Maybe physical laws are the same, but their ratios are different. So the sort of gravitational constant and speed of light may be very different in different universes. And because gravitational constant affects you and me, that's very important, because gravitational constant determines the orbit of Earth with respect to the Sun. If the constant is stronger, the orbit will be closer or further away. Remember, we discussed that part. So that celestial mechanics that is forming you and me as a biological species, so it actually will be affected, and the light will be affected of the energy that we will receive from the planet will be affected by the speed of light. And so there are lots of, if they will have different physical constants in different universes, they may be very different, very different life form being developed under those conditions.
Yeah, and that could explain if there's a kind of a universe on another dimensional plane. It could explain the dark matter. I mean, imparting that energy onto our plane, and then of course, then their plane would have 4/5 of matter and then 1/5 of dark energy.
But that will be in the different universe. We will not know that, right? So it's only if that if the boundary of those universes, and when I'm using the word boundary, I have to put quote unquote, because it's not, there is no physical boundary. So if we start sort of quote unquote touching the two universes, the presence of other universes may reveal themselves by clustering the galaxies or clustering the stars in a very preferred pattern. And if we observe the clustering in some way, or maybe a sort of non-uniformity of the early universe, that may actually represent the presence of other universes. So that's something we are looking at the cosmological data. When we are looking at the very early universe, we are looking at how uniform was the matter distribution at those early stages. If the matter distribution is very uniform and isotropic, you look at any angle, any direction, it's uniform and isotropic. And so that's what you expect from a single universe. But if there will be some clustering involved, that may indicate the presence that during the explosion, the universe actually, the explosion of the universe reveals the signature of the matter present at the time during the Big Bang.
Yeah, so, and this is string theory, or close to it, if I'm not.
String theory is something different.
Okay.
And so we are trying to explain how, what will be the next connection between the elementary particles. So it's not there yet. It's not yet connected to physical reality. It's a nice mathematical sort of exercise, extremely elaborate mathematics, and somewhere it connected to physics, but it yet to make a bigger impact on the physical theory. So, but string theory is an exciting area of physics that had a lot of promises about 20 years ago, maybe still, but those promises are not there yet, not material.
They're still working on it. Yeah, and I say that I mentioned a space particle because from where I'm looking at it, it's the graviton is obviously influencing space. So it must be influencing some entity of some sort, and so that's where I came to that. So that's just an interesting thought. Maybe we'll figure something out in the future, but maybe not. Um, and then in terms of the expanding universe, that's going to leave us if we extrapolate with that acceleration. Well, it gives us redshift, which is good because, and for the viewers, redshift is, and correct me if I'm wrong, it's the wave crest to wave crest of light quanta. We can understand that it's separating. So over time and distance, we can then see how far something is away from us, and then with spectroscopy, we can see what it's made of. So those are actually two amazing tools that the universe has given us. Anyway, the expanding universe is going to eventually expand, and it's going to rip apart elementary particles, and we're going to be nothing. How does that make you feel?
Feel good. Physics works,
Right.
and the reality is that look, it will happen many billion years in the future. And
Yeah.
so by the time I trust the humanity intelligence will find a way to exist. So I don't think we'll just give up easily. And I trust that we will be able to travel and to develop techniques that maybe identify better conditions. But let's leave it to the future generations. I think we'll have plenty of interesting and exciting work in the near future for us to deal with
Yeah.
in terms of exploring this universe.
Yep.
And that's exciting. Our models may be, projection of cosmological evolution may be corrected because we don't know if our universe is closed or open, or maybe it's a different models. So the way that some models suggest that it eventually expands and sort of expands so far, so that we'll lose causal contact with the stars. So more stars will be dimmer and dimmer and dimmer, and they will disappear, and then we'll be in isolation. That's a depressing picture. I don't want to see that.
No.
So, but it's only one of the models. So through our lifetime, we will not see that, but maybe 150 billion years in the future, the Earth and the Sun will be the only. Whatever will remain from the solar system will be the only part of universe that is observable. But that's only a theoretical model. We'll see how that will be corrected with the new knowledge that we'll collect by studying the universe around us.
And before the sun destroys the Earth, actually, the Andromeda Galaxy is going to collide with us, if I'm not mistaken, and we're going to have a whole new night sky.
Absolutely, there will be exciting processes around the solar system, around our galaxy, and so. But by that time, I definitely expect that humanity will be able to develop technology to travel and to survive. So I think basically for the last what we can extrapolate and realistically, one way of predicting future is looking at the past. And as we just discussed, it's not a good predictor because we can safely predict when the expansion is linear. And so you can predict everything, let's say, maybe starting 100 years ago, going from 100 years ago, going backwards. It's easy because expansion was kind of linear. But now expansion is very non-linear. And so predicting that will be very difficult, what future entails.
Yeah. And the SGL is a good step in that direction. And when you mentioned us moving to other planets, I mean, this is great for looking for life, but also let's look for planets that we can go to after Mars, right?
That's one point. Another point is there were many science fiction stories written, novels written in the past, suggesting that humanity will travel at ease between the stars. This is wonderful. but the practical steps towards interstellar flight were also kind of theoretical. People were relying on exotic means of propulsion, like antimatter propulsion, nuclear propulsion, and those propulsion techniques are feasible but not yet technologically achievable, some of them. And so that actually diminished our efforts and aspirations to leave the solar system. And why? Because basically, once you realize that Voyagers are at 150 astronomical units out from the sun today, and after that is just empty space. It's about 2,600 AU out before you reach Alpha Centauri. And you have to travel empty space, a lot of empty space. And the challenge there that once you realize that reaching the star, you have to develop. You have before you reach the star, you have to develop all that technology, and many people kind of lost interest because it's not practical yet. Solar gravitational lens provides you with the first stepping stone. It's a practical application that we need to develop technologies that will pull us out from the solar system exploration and going beyond. We are pushing technologies pretty much in every direction. Every spacecraft technology needs to be pushed. Power sources, communication, agility, autonomy, data analysis, navigation, survival, long-term survival in space. It's not a simple thing. So to develop that, it's a first step for humanity actually to do. And why we do that? To explore other worlds. So we have now a very clearly articulated objective to do that. It's not, okay, let's explore, let's go to next star. And how we get there, it's not important, but let's dream about it. No. We are not talking about this. We are talking about once you have a target, let's look at this target. And this is how we can do it. So that provides us with the motivation to make first practical step towards interstellar flight. And as you said, once we will look at those targets, there will be even more motivation maybe to visit them someday. And so we are now getting on a practical path towards interstellar flight. But the first step should be solar gravity lens.
How do you look at propulsion? Because even at the speed of light, it's going to be not easy for a team to get to another planet unless we institute cryogenic sleep or something like that. So how do you think of propulsion, and do you think we'll ever reach the speed of light or faster? And obviously, when I say faster, I mean that would essentially be cutting space and moving through.
Let me go back to the human beings. I think we were developed to fully benefit from the environment on this planet, and so we have a vertical posture, we have our vocal cords, we have two eyes to have depth. We have hearing. We are able to speak because we benefit from atmosphere, from observing through the air. So we live on this planet, and the physiology and metabolism all are adjusted to the solar environment. So now, when you leave the Earth and you fly in space, and my friend who visited space for stayed in space for a year, pretty much confirms that up in space, the most important part is the brain, because everything else is not needed to be in space, right? So we develop the way to walk and grab things because it's convenient for us to run away from the lion and maybe to grab a spear to get some food. But this is our life on this planet. When we're in space, the most important part of our body is the brain. Everything else is life support system, and so the life support system to live on this planet, right? When we start traveling, we don't need that life support system. What determines, what sort of differentiates us from each other, maybe our consciousness, and so our experience and life that what's need to be preserved. So maybe in the future, I expect that we will be digitized. And so maybe some biotechnology, so bioengineering and essentially artificial, in the information technology will be synergetically combined, and the human 2.0 will be digital. And so digital is one way of thinking about this, because we may not need our biological body to go there.
No.
Because traveling, we don't have to have a body. Once we reach the destination, we may have a 3D bioprinter to print ourselves for that environment.
Yeah.
So again, going back to the genetic code that is actually can be digitized, and can be sent, and can be three-dimensionally replicated or 3D printed for the environment that code appears to experience.
Yeah, the brain is everything, and when you say that, it sends shivers down my spine, because it's really science fiction, and but probably legit. I mean, and Elon's going to sneak into our conversation again with Neuralink. Of course, well, Neuralink and what he's doing there, and I mean, we could. My thing is probably, well, we're probably going to make a exact replica of a brain, except with components that are artificial and everything, and we're just going to have shells for bodies. And if we want to climb a mountain, then we'll have the strong shell. If we don't need to, we'll use the weak shell and all that, and we'll just use that. And I guess, I mean, with that capability, and if we can replicate neural networks that are in the brain with components that are not organic, then there we go. I guess we have it, and we can definitely travel long distances with that.
Exactly. Once you digitize, and we do this already, we explore distant worlds through light. So light travels. So when you digitize, you send bits and bits of information.
Yeah.
And so when those bits can actually recombine themselves, and you can send small spacecraft with propelled to fractional speed of light,
Yeah.
with elements of this genome, or sort of the genetic code that can replicate itself. And so realistically, technologies that we are experiencing now, they can be minimized, and so miniaturized. So all of that is a matter of technology. But in terms of science, I think we are able to build pretty much any parts of the human body artificially except brain, right?
Right.
So brain is a computer. At some point, computer will reach the productivity and abilities as we need it to. The next step is to trust that computer, and essentially to be able to understand what consciousness is, because what that is this only the set of chemical reactions encoded in our memory and the neural network, or maybe it's actually something that is replicatable and can be improved. That is an exciting area of research that is now ongoing. So I think in terms of building human bodies, printing, bioprinters, printing livers, printing, organs, we may be getting there faster than we think. And so I'm pretty much okay with us living longer and happier, because our lives will be more productive. And so that will affect our life on this planet. We have to redefine who we are. If we live longer, not 100 years, but let's say even 200 years, we have to redefine a lot of things, who we are and what we do, and how we build relationships, and how we establish our ethics and morals. So lots of human institutions will have to change. The society is now being not threatened, but motivated or challenged by the technology, because we evolve as rapidly as we are. And society is not yet recognized that we are now evolving much faster as a human beings as we were for the whole history of humankind. And so that is something, this is the debate that needs to happen, because where do we go? How do we actually evolve? And what is the right path for safe evolution of human beings, right?
Right.
Because ultimately, artificial intelligence, it may be a nice, catchy phrase, but ultimately we will surpass that.
Because I don't think our brain is even. I mean, if we were to, I think about this a lot. I think of consciousness a lot, and I'll touch on that. But I also think of like life extension, because there's a lot of interesting research coming out of Harvard specifically about life extension. And if we were to just in a snap extend our life to 200 years, can our brain even handle 200 years of memory
No,
and information? Because
no.
it's been evolved to handle 70 to 100. So what I mean, we might just go blank after 120 years and start forgetting things like a computer would if it's not ready.
I mean, if people will, if a person will be asked, would you like to live to 200 years? The answer would be yes, of course.
Yeah.
But then the challenges that uh, the person will experience are quite significant. For example, if only a fraction of people will be given a chance to live longer, so they will observe that some people going behind the horizon, right? So basically, they will be switched off in a sense, right? So that's emotional and moral dilemma that society is facing. And so, the wealth distribution on this planet is uneven, and because technology-driven innovations are pretty much bringing, access to wealthy individuals. So I expect that those individuals will get first lease of life, longer life, right? And so that will separate the society even further. So I'm bringing only one potential conflict within the society, and so we have to address this not only single nation but nations, because how do we deal with global wealth distribution inequality?
Yeah.
Because the problems that we face now in different parts of the world because of the COVID, they will be drastically amplified when we have access to, a digitally cleansing technology. You can potentially you can think about this, and I have to say this is not a NASA view, right? So this is me talking about this. It's not an official opinion of any organization. It's me and I talking about this. But basically, it is something that on the back of my mind because I'm looking for life in the universe. But we need to understand what life is and will be on this planet first before we'll make that contact with the life elsewhere.
Do you think life from another body has visited Earth before? Or I'll also add something to that, which I believe probably. Do you think an extension of life, so a drone or something to measure the atmosphere, just passed by? I'll add that as well. So a craft that's artificial or actual life itself.
The way you phrase the question, believe, right? To me, I delineate the two words, two phrases. I believe and I know, and I should say that I don't know.
Yeah.
So I mean, I prefer to phrase my answers and questions based on the knowledge I have, or maybe based on my approach, but my ideas, but not on beliefs, because beliefs are harder to verify. So yes, it's a very exciting question. There may maybe some indications of maybe some puzzles on this planet that may indicate that we were visited before, but I don't have a strong confirmation for that. It would be nice, but I just don't know, and I think nobody knows. So it's when you start differentiate. I believe and I know. When people will be pressed to say yes, many of them will be believing, and I don't really fall into this category.
No. Yeah. Yeah, it's tough because it's very easy to fall into a trap of listening to all this, a lot of the stuff that's obviously not real, and wanting it to be real, and then a lot of people do that, and then there's the crazy stuff with Commander Fravor and all that stuff that's happened, and people who actually have merit saying they're seeing things. I don't think if life has the ability to make propulsion technology to get here, they wouldn't need to come here. Just as we explore Mars, Venus, and beyond with our sensors and craft, I think if anything came here, it was simply something to aid in maybe mapping the galaxy. They're probably mapping each planet and just seeing what it's made of and moving on to the next one.
Right.
That's what I think.
And that spacecraft, quote unquote, visited us recently. I would say, why didn't they stop? So the interstellar asteroid that was suggested to be like an interstellar spacecraft visiting us.
Well,
Why didn't they stop? It would be nice to chat with them. So, but instead they just marched along their trajectory, went away, disappearing from us. It's just sad if aliens are such sort of they're that uninterested in talking to us. That's sad, right? So it's not a
Right.
good message. I would prefer them to stop and say goodbye, so say hello.
Yeah.
So, but they didn't. So in general, I don't think that we have evidence for any yet extraterrestrial life. So, and I would like to have, sort of to be able to see it, to be in contact with it. But at this moment, we just don't have evidence for this.
Yeah, and with us looking, I mean, how do we know even what to look for if there's advanced life that is just beyond our comprehension? Just like a bird outside landing on my car, it doesn't realize that that's an artificial thing. It's just a part of the environment. So how do we even think about that? It could be right next door, and we just don't know.
But still, it's a process, right? When you're a child, you are exploring your world. You are seeing faces of your parents, your friends. You're exploring your kindergarten, the school. Your life expands as you grow, and we are in that scale. We are children in the universe. We are exploring the world just around us. As we grow in our appreciation of life in the solar system and start sort of growing further, there will be other experiences we'll go through, and so it's just something that just give it a time. And I'm sure, I trust that intelligence that has on this planet and the human beings will be able to appreciate where we are and to develop new tools to explore not only life, not only the solar system, but actually the universe beyond the solar system in the galaxy. And so it just give it a time. And I guess what is important is to ask the question that may have an answer given the technology level, right, that we have. Because if 200 years somebody would ask a question whether or not there is exoplanet exists, the answer would be absolutely no. Because what is exoplanet? Why do we need exoplanets? Or maybe let's say maybe 3,000 years ago, or maybe even deeper, the Earth was the center of the universe, right? And remember those elephants and the tortoises that where elephants stood and on the tortoises. And when you ask where is that, what is behind that tortoise? There is another tortoise, even bigger. And what is behind that? Oh, the answer would be, come on, trust me, there is some more tortoises behind.
Yeah.
Later on, we learned that we are not center of the universe. And so we are orbiting the sun. And even the sun is not the center of the universe. And even the galaxy is not the center of the universe. We have to let it go to become the most important part of the universe. We have to accept the fact that we are part of something larger. We need to appreciate that and start to learn step by step, asking appropriate questions given our understanding and our access to technologies. And don't be shy. Ask those questions and try to get answer. So it's part of growing up. And our society is still too young. Let's say it's only 70,000 years separates us from our ancestors in the savannas of Africa.
Yeah.
But now we actually are capable of flying spacecraft and this debate with those very questions that actually made us intelligent.
Yeah, and so I think what you're saying is the more data we have, the better we can situate ourselves to start asking questions, and we don't have even maybe 1/10 of the data where we're at. We need to grow up as humanity.
Look, science is important, and I guess what we have to realize is that the growth in the society will be technologically influenced. So we are all interested in economic growth, and economic growth used to be related to natural resources, right? You extract more oil, you extract more gas, you extract more resources, you sell them, and that's how you build your economy, or you build something.
Yeah.
You build houses. So, but the growth is not sustainable because we have so many people on this planet, and the population grows quite significant. The energy consumption grows non-linearly. If you look how many petajoules of energy humanity consumes every year, and that's going exponentially. Where do we get that energy? So if we are still extracting oil, well, how do we do this? How do we sustain life on this planet? So what I'm saying is that we have to trust science and technology to develop the sustainable growth path so that it will allow us to preserve the natural beauty of this planet and still develop technologies that will allow us to grow economically and develop other things. Potentially, remove sort of putting all the industry in space, in maybe close to the moon, maybe in orbit around Earth, so that we will not pollute our environment and benefit from the infinite amount of energy that is coming from the sun. We start to need living off the sun,
Yeah.
because now we live off the planet, and
Yeah.
so we exhaust the planet. But let's start living off the sun because this energy is available. Once we do that, I think we will benefit from preserving the planet. We will not pollute it as much, and our appreciation to the life will improve because environment will be cleaner. We'll live longer because environment is much cleaner, right? And that's something that's very important. We have to realize that what drives life is the energy, access to energy. Life began on this planet because the sun produced a lot of energy. Thermal energy from within Earth helps sort of provide conditions needed for life. Now we need even more energy that we used to have because our technology drives us to cars and electricity and production plants and everything drives energy. So we need to find new sources of energy.
Yeah, we're good with the sun. The sun can it provides the world as much energy as we need, no matter how technologically advanced we get, many times over. If we can replicate on an atomic level the process of photosynthesis that plants have achieved over millennia of evolution, I think we're good. And of course, the moon has craters with water ice that we can harvest and take things out on a molecular level and then get fuel. So we don't even need the Earth anymore, which is sad, but also good in a lot of ways.
Well, in a sense, I expect that in the future, in the very near future, let's say maybe within maybe 5 to 10 years, there will be those commercial space stations orbiting Earth, so that people will start visiting space and will start looking at space as a potential habitat. And so, the more humans will be visiting space, the more we will appreciate how fragile the environment here. And maybe this is where our psychological transformation will begin. We need to preserve this planet because the recent summit about global warming pretty much resulted in the less expected than the progress of we expected more from that meeting, but it resulted in what it resulted. So it's really we need to do more. We need to do more to preserve the planet. But yet, how to actually stop us to appreciate the environment to preserve the planet? We need to educate the kids. So
Yeah.
our important step is the education. So I guess maybe we need to invest more in educating, providing kids with information how fragile environment is, so that the new generation of humans on this planet will be more careful, and they will be first of all we discussed that they will have access to space. As they grow up with knowing that space is there, and then they will also be driven by trying to preserve the environment. So this is a hope for the society. So there is a hope for this planet in the younger generation that is actually very sensitive what we have done to this planet, and so we need to help them to succeed. That's very critical.
Yeah, and in a good direction. I mean, it looks like we're going in a good direction with what NASA's doing, what you're doing, and with what planetary biologists are doing, and because all those people and what you're doing is there's no ROI that's attached to that you can attribute to, like, this is where we're going, this is what these are what resources we're going to get. It's driven by 100% of curiosity, and if we can create a culture around breeding curiosity, we'll do more of these, and we'll send more, because these, as you need to get paid. The people who need to get paid that are on your team, resources and engineering needs to get allocated. Resources at the end of the day tax dollars need to go towards this, and it's a beautiful thing that it's already happening with what you're doing
And
based off
it's
curiosity.
And it's a process that actually is generated by the society. There is a demand within the society to learn more about the environment because the longer we live, the more we learn about our environment, and the more, I mean, there is a more demand on how clean the environment should be, and who is a better position to answer those questions, the NASA. And of course, the way we do this is we get the request from the society through multiple meetings, through multiple, um, uh, uh, subjects where the environment is important. So we get ultimately we get our funding appropriated by Congress, where we actually propose how to address those challenges. And so, National Science Foundation and NASA are the two primary two agencies that actually delegated to address those questions. NSF does this within the Earth, and NASA does it from space. And the collaboration between the two addresses this problem in a global scale. And we are learning a lot. We are learning about the very fragile environment. It's not a very simple system. Studying it, we just begin studying it. And this year, Nobel Prize was in physics was awarded by to the group of scientists who developed very elaborate models for that are describing environment on the planet Earth and how it's been affected by multiple factors, which is very complicated model. But in fact, this model was verified and is now being used to guide our resources and future directions. In reality, this is a very important topic that NASA is addressing. So we have a fleet of spacecraft that is orbiting Earth, looking back at Earth, and studying, monitoring Earth pretty much in real time. We are studying oceans, we're studying atmosphere, we're studying a lot of important trends and dynamics in the planet, like studying the tectonic plate motion, studying the continental drift, studying the orbit, the rotation of the planet, the interior of the planet, atmosphere, oceans, and the interaction of all those various systems, which is critical to understand what do we humans bring to this environment. Because once the planet is understood, we are very disturbing contribution because we build factories that pollute, that bring a lot of CO2 in the atmosphere, and this CO2 affects global circulation. And now, once we need to do something more about the planet survival. And so, yes, and I agree with you fully that NASA is doing a lot of good work here. So I'm happy that our agency is contributing to this very important effort.
Yeah, and tying it back to SGL, are you talking to any other countries, or is just you guys working on it?
This mission is of global importance, and we are collaborating with a lot of European institutes. And essentially, what I'm happy with, there are several PhD students and several groups in the Netherlands, in Germany, in France, England. They have contacted us, and they're now they're asking how they actually can contribute into developing instruments and studying solar gravity lens as a mission and the physics of the SGL. There are some Canadian friends, there are some Latin America, and the effort became global. And our idea is that this mission is of importance for the humanity. It should not be done by only one nation, but as a collaboration effort. So from the beginning, we are open to collaboration. We hope that only by doing this on behalf of humanity we can achieve this mission, because it excites, it resonates with people of every country on this planet. Because again, we all kids at heart. We're all 6 years old. We're just growing older, but our appreciation of this planet and our all sort of our excitement about the universe is never ending. And so it doesn't matter where we live. We're all interested in doing this. And if we can do this together, the faster if we can do this together, this is the only way to actually succeed.
Yeah, a conglomerate of people and resources is probably going to accelerate this. instead of just.
Absolutely, absolutely. But I guess in this case, because it is funded by NASA at the moment, so NASA takes the leadership role, guiding those efforts and establish and helping us to establish those collaborations. Because it is something that our team is doing now, because we are contacted by philanthropic organizations in United States, in Europe, that they would like to be part of our efforts, and so they are willing to contribute some funding to fly those spacecraft that will reach high velocities. And so there are some, federal agencies, there are some organizations that are interested to be part. And so this is a second year of our effort that is funded by NASA, and our task is actually build successful public-private partnership to enable transition of this effort from within NASA to a global scale, so that we will be able to fly that mission to the solar gravitational lens by the year 2036.
2036. Okay, interesting. I didn't know there were some private funds that are. Can you name some of those funds? I'm curious.
Breakthrough Initiatives is one of those organizations that are very interested, because Breakthrough from the beginning, they were supporting us within through the all phases, because our objectives and theirs are very synergistic, because they are interested to fly as a laser-sailed spacecraft to Alpha Centauri system and reaching very high velocities. And in our case, we are aiming at a larger set of targets, potential targets. So in a sense, there are some technologies that they will have to deploy are very synergistic to our solar sailing technologies. And maybe our technologies will be demonstrated first, and then they will be able to benefit from experience that we gain. So for them, it's the technology demonstration missions that we are going to be flying in the next 2 to 3 years is the key for them to learn about the environment and to move forward into, to deploy their system. And so this is one organization there. We're also in discussions with Boldly Go. It's another philanthropic organization that is interested to help structure our efforts and maybe serve as an organizer of the efforts in a global scale as well. So there are other organizations in the United States that are actually helping us to do this. There are some federal agencies that are stepping it in, but we are in discussions with multiple organizations. And so it is something that is very exciting because, look, the objectives for the mission are quite they're appealing to many people, and that's why I think we have a very strong foundation to develop a successful public-private partnership.
I couldn't imagine an individual saying, "No, I do not want to see exoplanet up close." I think everyone can relate to how interesting this is, so that makes a lot of sense. So let's talk near term. What are you up to nowadays, and what's the team working on now?
We realized that we have a very unique mission design aspect because navigation was a critical component. How do we actually navigate spacecraft? Because once we reach the 650 astronomical units, when the science operations will begin, there is no celestial body that we can use to navigate against. Typically, we do navigation with solar system bodies within the. When we fly to Mars, we use Mars as a reference body to navigate against. And flying to the moon, we navigate toward the moon. But there is only light field. Solar gravity lens is a projector, that projects a light field into the deep space. And so to get there is no anchor. How do we actually find that light, and how do we navigate? And what we realize that solar gravity lens helps us because we have a highly amplified light from the host star that can be used as a beacon. So once we reach the focal region of the solar gravitational lens, our spacecraft can use the amplified light from the host star and build something we call local reference frame. And with the local reference frame, we can then find the exoplanet and move within moving image of the exoplanet. As we discussed in the past, nothing is static in the universe; everything is moves. So the exoplanet orbits its host star. The host star moves with respect to the sun. Even our sun is not fixed in space because it moves under gravitational pull of Jupiter, Saturn, Neptune. So there is all the motions involved, and so image is not fixed in inertial space; it moves. So we need to be able to navigate and be always on that image. And so we realize that the solar gravity lens helps us to do just that, because it amplifies light from the host star that can be used to position our spacecraft within image. And we don't need very elaborate, very sophisticated acceleration propulsion technique. It's only 5 microns per second squared, which is needed for the acceleration for the thrusters. And electric micropropulsion is completely capable of doing just that. So that is exciting element for the mission development, because it simplifies the concept of operations in the focal region of the ASGL. So now the team is focusing on developing concept of operations, simplifying drastically the need to maintain and keep the local reference frame, and that is now becoming very feasible. So we are working towards simplifying the concept of operation and actually optimizing it so that we can do this within maybe 2 to 3 spacecraft orbit, sort of moving in this region. So, and then we are building now the technology demonstration mission prototype, and we will go through a sort of, we will defend this prototype in front of the jury of experts in the next 6 months. And by the time we complete the effort, the NIAC effort is within 11 months, we will be able to start developing the actual flight mission for the technology demonstration mission. And that will culminate with a few TDM flights in the near, maybe 3 to 5 years. Once those technologies are being proven and we are able to demonstrate high transit velocities at the level from 7 to 10 to 15 astronomical units per year, then we are ready to fly SGL. So our objective is to demonstrate solar sailing as a key technology for propulsion, because it's most feasible. There are plenty of other technologies that are being discussed. Chemical propulsion, which is limited in capabilities, not suitable for our purposes. There is nuclear propulsion. Technology readiness for that technology is not yet fully at hand. It will take some time to develop. There are other technologies, and solar sailing seem to be the most promising technology that will enable us to fly the mission when we need to. And so the next step here in the next few months, we actually will be able to build a very complicated simulation model that will simulate performance of the mission, including all the parameters involved, and sort of a lot of noise sources involved in terms of data analysis. So the spacecraft are not perfect. They will produce some outgassing for thrusters. There will be some errors in position determination. There will be some noise sources from coronagraph. Building all that model, including the signal and all the various sources of noise, that will bring realism, even more realism of the model. So once we have that realism, we will understand what the mission features might be. So far, we are aiming at flying a mission. Transit time to the solar gravitational lens focus will be in about 20 to maybe 23 years, and about 10 years of operation. So within 35 years after launch, we should be able to get that, a lot of information about that planet. But I would say in about 35 years, you and I will be able to see first images of exoplanets. That will be a reality. No other technique can achieve that. And so we are confident that solar gravity lens is actually the technique that will allow us to provide high resolution imaging of very tiny fireflies that are flying the searchlights in our stellar neighborhood.
Okay, yeah, I think we can wrap it up there. Good luck with that near-term project, and Slava, thanks so much for coming on. This was a really interesting conversation, and looking forward to having you on in the future.
Excellent, Taylor. Thank you very much. It was very nice be here, and so I'm excited that we are in a very interesting period of our lives where things that used to be science fiction now becoming a reality, which is quite exciting. And I'm happy to be part of those efforts in multiple situations. Solar sailing used to be discussed by Jules Verne, It's a French science fiction writer. And then it was proposed by multiple other important figures into technology. But now we are aiming at using solar sailing as a main propulsion technology. And also solar gravity lens is another exciting science fiction idea, pretty much almost science fiction, but now we're folding it into realistic mission design. And so the very mission to fly into 650 astronomical units away used to be also a dream. But all of the three dreams that I just highlighted, they're now solid engineering efforts. So with those solid engineering efforts, they will culminate in the mission design. And within our lifetimes, we should be able to see an image of exoplanet. Thank you very much for having me, and thanks a lot.
Thank you. I can't wait. It's going to be awesome.